Hello, everyone. Welcome to the tutorial entitled Contrastive Data and Learning for Natural Language Processing at this year's 2022 NAACL. The material that you will be hearing about today has been organized by Rui Zhang at Penn State University, Yangfeng Ji at University of Virginia, Yue Zhang at Westlake University, and myself also at Penn State. While contrastive learning has been around for a while, it's been gaining momentum. Why? I believe that's largely because it addresses a dilemma that while the representations learned by neural models have grown increasingly powerful in their generalization ability, we know that these models hide woeful reliance on spurious associations. And that's one of the things that contrastive learning tries to deal with. Now here we see an image of the tutorial website, where you can access all the materials. And I take little credit for the fine organization here. I hope you will be as impressed as I am with all the work that my co-authors have done to assemble these materials. The tutorial came to be in part because some of the Penn State NLP students used contrastive learning. So a little advertisement here. An example is Sarkar Das, whose paper on few-shot NER is in this year's ACL. Yue Zhang used contrastive learning a while ago for abstractive sentence summarization in 2019 EMNLP paper. And then much of Yangfeng Ji's work, especially on discourse and dialogue, investigates related issues of how to improve learned representations. Here on the next slide, I'm showing one way that you're likely to benefit from this tutorial, if from nothing else, which is access to this very thorough resource of materials on contrastive learning. It's very diverse. It includes survey papers, other tutorials, and blogs, as well as a large set of papers that have been categorized into more than a dozen categories. I'd like to say I'm particularly excited by this topic because of its connection to two areas that I've been very interested in throughout my career, which are evaluation and human cognition. Solid evaluation, benchmarks, and metrics are essential to the success of NLP. And in my view, it's no accident that contrastive learning bridges methodological questions about the design of our learning models through better loss functions or latent representations of the context that language is conditioned on, and also practical questions about the design of appropriate training and test data. Given that we can't inspect what neural networks learn, it's important to have the kinds of evaluation tests that can tell us that the model behaves well, not only on typical examples, but also on examples that deviate from type in critical ways. The many variants of contrastive learning share the intuition that embeddings of language examples will be more effective if examples that are near one another in vector space are semantically more similar, and on the other hand, if examples that are distant from one another in that vector space are semantically more divergent. Recognizing similarities and differences is essential to human cognition and therefore to human language use. Work in cognitive psychology by Eleanor Roche throughout the 70s on categorization and cognition proposed two essential cognitive principles that I would like to mention here. First, that the categories that we develop to understand the world should provide maximum information for least cognitive effort, which pertains to the efficiency of our cognitive processor. Second, structure and organization is inherent in the world, thus categorization pertains to our ability to function effectively in our environment. And at base, categories arise from similarities of items that are within the same category and their differences from items that are outside that category. Contrastive learning also incorporates similarity and difference into learned representations. Therefore, it implicitly builds in distinctions that are important to human cognition. We will now turn to the three parts of the tutorial with Rui Zhang presenting the foundations. Thank you.
So first, what is contrastive learning? It is a simple representation learning strategy introduced in 2005. The basic idea is to learn embeddings such that similar data sample pairs are close, while dissimilar sample pairs stay far apart. For example, suppose we want to have embeddings for these images. Then after normalization, we want to have embeddings of dogs on one side of this unit sphere, but the embeddings of cats will be on the other side. To be a little bit formal, so we can consider 3 examples. So X is the anchor point, X plus is the positive examples, and X minus is the negative example. Then if we have an encoder function F, such as neural networks, and also we can define a similarity measure, such as inner product, then we want to have the similarity of positive example to be larger than the similarity of the negative example. So contrastive learning has been first used in computer vision. And the most famous example is SimCLIR in 2020. They first used many different ways of data augmentation to produce different views of the same image. Then they use contrastive learning objective to make sure the representation from the same source images are close, but the representations from different source of images will be far from each other. So in fact, contrastive learning has been used in NLP in very early times. So after some literature search, we found that in 2005, Smith and Eisner introduced contrastive estimation as an unsupervised training objective for NLP to train log linear models. So I believe this is the very first NLP paper using contrastive learning. So Word2Vec is arguably the most successful example of contrastive learning for NLP. So the idea is, given the current word, the objective function is to maximize the probability of its context words, while minimizing the probability of random words by negative sample. So the positive examples here are, context words, but the negative example here is random words. And also the encoder function is the mapping of words to their embeddings, and we use inner product as similarity measure. So as you can see, contrastive learning is not a really new idea for NLP. So why do we give this tutorial today? So here we count the number of papers with titles containing contrastive learning in recent NLP conferences. As you can see, we found there is rapidly growing interest in this technique among the NLP community. Also, we count the number of papers in different fields of NLP. So as we can see, contrastive learning is still most used for producing text representation, such as sentence embeddings, and used for classification. But it also being applied in many other tasks as well. So basically, there are 2 general trends, as we can see, to how people use contrastive learning for NLP tasks. So first, the trend is we start from word embeddings, but then we, move on to use contrastive learning to produce general sentence representations. And recently, it has also been used in many other NLP tasks, such as question answering, summarization, text generation, vision in language, right? So that is the first trend we have observed from the previous 2 slides. So the second is, as contrastive learning is a representation learning algorithm, people first focus on performance improvements, but later it has been used to produce other desired characteristics as well, such as we can produce general purpose sentence representations, and we can also use contrast learning to improve data efficiency in zero-shot and few-shot settings. And we also will see some examples of using contrast learning for interpretability and robustness of NLP models. And finally, we also want to talk about some, faithfulness issue in text generation. So given this, here is our agenda for our tutorial, right? So Becky and I just finished this, introduction. And then I will first talk about foundations of contrast learning. So we will see some topics there. And in part 2, Yangfeng and Yue will discuss the application of contrast learning to NLP. And finally, we will give some summary and reflection. Okay, so let's go to part 1 first, foundations of contrast learning. So a quick recap, we talked about what is contrast learning. So it aims to learn embeddings such that similar data sample pairs are close while dissimilar sample pairs stay far apart. And if you look at this picture, to achieve this, there are actually 2 essential elements in contrast learning. So we break this down in 2 parts, right? So the first element is how we can create contrastive data from which we will learn embeddings, right? So the first part is about data. The second question is how we can design contrast learning objective functions so that we can really push embeddings closer or far apart, right? So the second part, the second element in this picture is the objective function, right? So yeah, so we will talk about each separately later. So we'll talk about several things in this part. And to answer these questions, we will first go to contrast learning objectives, and then we're going to discuss contrastive data sampling and augmentation strategies. And finally, we'll also give some analysis to better understand when and how contrast learning will work. Okay, so that is outline for this part. Okay, so let's go to the first bullet point, which is contrast learning objectives. So in this part, we're going to see several ways to do contrast learning objectives, right? So we'll cover several loss functions, and this is an overview. So even though there are quite a few of them, they are actually more or less similar, and we will summarize their difference later. Okay, so the earliest loss function for contrast learning is called contrastive loss. So as we can see from this figure, contrastive loss operates on pairs of example, right? So for example, we operate on x1, x2, they are from the same class, so there is a red edge between them. So that is the first pair. And we also have x3 and x4 are from different classes. So that is a blue edge, and this is the second pair. And we also have x5 and x6 from the same class. So this is the third pair. So contrastive loss is working as follows, right? So if 2 examples are from the same class, then we will minimize their embeddings. And here we can use, for example, L2 loss, right? So if this indicator function is true, then they are from the same class, then we're going to minimize their embedding distance measured by L2 distance, right? So, and otherwise, we're going to use a margin loss to keep their distance at least margin M, right? So that is the earliest loss function, which is contrastive loss. The second loss function is called triplet loss. So, in contrastive loss, we look at individual pairs, right? So if the pair is positive, we go to the first term. And if the pair is negative, we go to the second term of the loss function. But triplet loss works in different ways because they directly work with triplets of data points. For example, what I mean by triple is a 3 data points, right? So x is the anchor point, x plus is the positive point, and x minus is the negative point. So our goal here is to make sure anchor is much more closer to positive than to negative, right? So this is the starting picture. After learning using triplet loss, we want to have this picture, right? So, and we achieve this by minimizing this triplet loss. So this is the triplet loss. So here we have just the one single term, which is max margin term, right? So if the loss is 0, then that means the distance between positive and anchor is smaller than the distance between negative and anchor by at least margin n, right? So if that is true, then the loss is 0 and we are good about this, right? So otherwise, there will be a non-zero loss value to minimize until we got this picture, right? So that is triplet loss. Okay, so we have seen 2 loss functions, right? So contrastive loss and triplet loss. And in triplet loss, it only has one single negative example, right? So if you have 3 data points, there is only one negative. And we can really look beyond just one negative example, and we can generalize this by considering one positive example and multiple negative examples, right? So in this case, we're going to use n-pair loss, right? So this setting becomes very similar, as you can see, to a multi-class classification, right? So there are n examples, and we want to pick one positive out of the remaining ones, right? So the n-pair loss will do this. So it uses inner product to calculate similarity, and then use this softmax loss function to optimize their embeddings, right? So this loss function is similar to softmax loss for multi-class classification. So that is n-pair loss. Now we come to a broader category of contrastive learning loss, which is NCE, right? So noise contrastive estimation. So it is originally proposed for estimating parameters of some statistical models. So in general, suppose we have a target distribution that we want to estimate, and we got some positive examples from this, sampled from this target distribution. And we also have some negative samples from a noise distribution, right? So that is the setting. The idea of NCE is to run logistic regression to do something like binary classification so that they can differentiate positive samples and negative samples. So here we use L of x to denote the logit function of a sample from the target distribution, right? So if that is logit, we can take the sigmoid of this logit function, and that will give us the probability of a sample coming from the target distribution, right? So given these notations, we can define NCE loss function as follows. The loss function will be similar to the standard logistic regression. If the sample is positive, we maximize its log probability. But if the sample is from the noise distribution, we use log of y minus its probability, right? So this is just a logistic regression. And we can even simplify a little bit like this to replace log of y minus sigmoid to be log sigmoid of minus of this logit. There are actually, so this is original NCE loss function, right? So it's very similar to logistic regression. And later on, people have proposed several other variations of this NCE loss function. And we will see some of them later. In fact, many people just call all of them NCE function, loss function, right? So, if you see NCE, it probably refers to a broader category of loss functions following this idea, right? So that is NCE. Okay, so what is some variations of NCE? So actually, the word-to-vec algorithm uses NCE to learn word embeddings, right? So here in this picture, we have this scikit graph model showing on the right, right? So the logic here is the inner product of two word embeddings, right? So given the current word, the positive samples is context words, and we use their inner product to measure their distance. And we also, so that's the first term, right? So for the second term, we also sample many, negative samples to do some random sampling to get some random words as negative samples. And the objective here is the same as previous slides, right? So we want to maximize the log probability of positive pairs while minimizing the log probability, the log of y minus probability of negative pairs, right? So they are really similar, except that now we have multiple negative samples, and then we can sum over those negative samples, right? So that is negative sampling objective, which is used to optimize word-to-vec embeddings. Okay, so that is probably the first variation, negative sampling. The second variation is called info NCE, right? So if you think about the vanilla NCE, it works only with one noise samples, right? So and it uses logistic regression to do binary classification, right? So because there are just two positive and negative samples, right? So here for info NCE, the idea is to generalize to multiple noise examples, right? So then, if vanilla NCE use logistic regression, then info NCE will use softmax loss to differentiate a positive sample from a set of noise examples, right? So that is the idea. Info NCE is first introduced in this paper called Contrastive Predictive Coding in 2018. And formally, we're going to have a so-called, they will call this context vector. But in our case, you can think of this context vector as the anchor point, right? So that is the context vector. And then we're going to have a set of samples, right? So we will have n samples, including one positive sample and n-1 negative samples. And then the info NCE loss will look like this. We're going to have a scoring function f is a function of a pair of x and c to measure their relationship or their, you can think about this as similarity measure. Then we can define this softmax function, right? So we, on the numerator, we have the positive sample, and we divide this by the sum of all samples, right? So if we're going to minimize its loss, we essentially maximize the probability of our model predicting this positive sample correctly, right? So very similar to multi-class classification. Okay, so that is info NCE. To be a little bit more concrete, in many applications such as same CLIR, they use a so-called normalized temperature scaled cross entropy, right? So it is insertionally info NCE, but you use several different ways to really implement this loss, right? So the first is they're going to have cosine similarity on normalized embeddings, right? So, and then after this, they will divide it by this temperature parameter and take the exponential of that to be our scoring function, right? So here we have a new parameter, which is tau, is the temperature. So temperature controls the relative importance of the distance between pairs, right? So if you change the temperature to be low, then the loss is very sensitive to the small distances, right? So on the contrary, if you change the temperature to be high, the loss is dominated by the large distance, right? So that is normalized temperature scaled cross entropy. So that is very practical info NCE version. Okay, so later we're going to, we also have this idea to extend, different numbers of positive examples in a batch, right? Not just one, because in NCE, it has many negative examples, but it only has one positive sample. And here we can have many positive examples as well. For example, if we have m positive samples and negative samples, we can define this so-called soft nearest neighbor loss as follows, right? So here it is very similar as before, except that we use L2 to measure their distance. And also on the numerator, we're going to sum over all m positive examples, right? So this is called soft nearest neighbors loss. Okay, so the last, loss function is called lifted structured loss. So this figure compares contrastive loss, which is our first loss function, and the triplet loss, which is our second loss function, right? So just a recap, contrastive loss looks at individual pairs. But triplet loss will look at a triple of data points, right? So, but they only considers single pairs or just a single triple, right? So that is their contrast units, right? So that is their limitation, because as you can see, suppose in a training batch, we have 6 examples in this batch. So x1, x2 are similar, x3 and x4 are similar, x5 and x6 are similar. Then we can not only consider individual pairs, but we want to explicitly take into account all pairwise edges in this picture, right? So including 3 red similar pairs, but also many other dissimilar pairs, right? So that is the idea of lifted structure loss, and we want to consider all pairwise edges in this batch. Okay, so that is a good motivation, but how we can do this? We can do this as follows. So we're still going to start from the triplet loss, right, which is the max margin loss, but we're going to replace some terms here, right? So to really understand how this works, suppose Dij is the distance function between 2 data samples, xi and xj, right? So then, we can look at, one particular positive pair, which is x3 and x4, right? So their distance is this first term Dij, right? So this is similar to what we had before. Then for the second term, it has some, something here, right? So for the second term, because there are many negative pairs, we want to find the most difficult one, right? So therefore, we're going to calculate all the other distances between negative pairs, right? So there are 4 over here and 4 over here, right? So there are 8 distances between negative pairs, and we want to take maximum over them, right? So that's why we can take maximum to find the hardest negative. So when we take the maximum, we actually use the most difficult negative examples in our loss function. Okay, so this loss function is hard to optimize because it is not a smooth function, and in practice, the author also found it may converge to that local minimum, right? So therefore, they relax this by replacing this max with the second term as this one, right? So this is given a smooth upper bound to make sure our optimization is easier. Okay, so that is lifted structure loss. Okay, so as we can see, there are many different loss functions we have introduced, right? So probably you feel a little bit tired of this. So here we want to summarize this part by putting all loss functions in a single table, right? So in this part, we have described several different contrastive learning objectives. And actually, if you think about those learning objectives, the idea is pretty much the similar, right? So sometimes their difference is very subtle and very small, right? So to better clarify everything, so here we make a table to compare them, right? So we show their name and the original paper they are from, and also we list their contrast units, and maybe some of them are looking at pairs, but others are looking at triplets, but maybe others looking at sets, right? So that is contrastive units. And also we're going to look at the number of positive examples and also the number of negative examples, right? So finally, in the last column, we also show some other famous applications where these different loss functions are used, right? So that is our summary for this part. Okay, so that is our first part. In the first part, we discussed the first element, which is contrastive learning objective, right? So, and in the second part, let's come to the other side, which is contrastive data. So the question for this part is, how can we create contrastive data so that we really have the material from which we're going to run these objective functions, right? So most contrastive learning frameworks are self-supervised learning. Basically, they use data augmentation to produce positive pairs. And then you use random sampling, such as in-batch examples, as their negative pairs, right? So this is self-supervised or basically unsupervised. So the biggest advantage of doing this is that we don't really need labeled data, right? So no label is required, and that is why probably why contrastive learning is so attractive, because they provide a simple strategy to learn representation from unlabeled data sets. Okay, so but if you think about this, there are also several challenges to make such self-supervised contrastive learning work, right? So here we have 4 challenges that we want to discuss. The first is non-trivial data augmentation, right? So that means we need to have some clever data augmentation strategies, and especially for text data, we need to make some non-trivial changes of examples, but we don't really want to modify their semantic meanings because we're going to form positive pairs, and we don't want to modify their semantic meanings. So that is the first challenge. The second challenge is the risk of sampling bias, or basically the risk of false negative. So what does that mean? Right, because we random sample negative pairs, right? So it is very possible to have some false negatives, right? So this is called a sampling bias. So they are, we treat them as negative, but later on we found that they are actually also, should be similar to the anchor point, right? So that is the risk of sampling bias and false negative. The third challenge is hard negative mining. So hard negatives, is some negative samples. They should have different labels from the anchor point, but their embeddings are close, right? So that is why they are hard to optimize, right? So finding hard negatives is very important to make contrastive learning effective, right? So that is the third challenge. The fourth challenge is many people report that in practice, they find large batch size is really important. So this is because when we use in-batch negatives, large batch size can cover more diverse negative samples to provide meaningful learning signals, right? So that is, a list of 4 challenges we want to discuss to, make sure self-supervised contrastive learning really work. Okay, so that gives the outline of this part, right? So for this part of contrastive data, we're going to start from the self-supervised contrastive learning and look at each of the 4 challenges more closely. And finally, we're going to talk about briefly the other, the other alternative to self-supervised version, which is supervised contrastive learning, right? So that is the outline for this part. Okay, so let's go to the first part, right? So which is on data augmentation. So in this part, we want to discuss some data augmentation strategies, especially for text data, right? So data augmentation aims to introduce some variations of the text input, and hopefully through these changes and variations, we're not going to really modify their semantic meanings, right? So that's why we can form a positive pair. Okay, so in this part, we have such simple, taxonomy of 3 different ways we can perform, data augmentation on text. So the first category is on text-based, right? So we look at either token or the sentence, and we can have token level, lexical editing, or we can change the entire sentence using back translation. So that is text-based data augmentation. We can also do data augmentation in embedding space. So that is, we first put text into some neural network, for example, to get some hidden representations, and then we're going to do something over these embeddings to, produce other augmented data, right? So in this part, we're going to look at 3 methods, including drop out, cut off, and mix up. And finally, we're going to briefly mention the manual way, right? So that is, we can, basically manually write more diverse paraphrases for the text as data augmentation strategy. Okay, so the first one is lexical editing. So lexical editing means we perform some operations on tokens to modify the text, right? So in this paper, easy data augmentation techniques for boosting performance on text classification tasks, they summarize really 4 operations they can use. The first operation is synonym replacement. So that is you pick a non-stop word from the sentence and replace this word with its synonym, right? So you can look up a synonym from some maybe the thesaurus or some WordNet resources. The second operation is random insertion, right? So basically we will pick a random position and insert a synonym of non-stop word, right? So this example of random insertion. We can also do some other operations such as you can random swap 2 words, or you can random delete some words. So in this figure, we show how to apply those 4 operations in this example input sentence so that you can create some variation of those sentences, right? So that is lexical editing. So the lexical editing operations are simple, but they are random. So they focus on, individual words and do some random operations. We can also incorporate some contextual information to do word replacement, right? So that is the idea of so-called conditional BERT, right? So in this example, they introduce conditional BERT to perform contextual augmentation on labeled sentences, right? So as this figure shows, if we want to replace a word good in this sentence, we put the sentence label positive in front of it, and we mask this word good as the input to the BERT, right? So the model architecture of BERT is still the same, right? Except that we're going to add this label embedding for each token. And the masked language model will help us finally choose another word for replacing this input good, right? So because the input is conditioned on the sentence label positive, we can make sure the BERT will choose an appropriate token for replacement without changing the sentiment of the label, right? So that is word replacement using this CBERT idea. Okay, so the next approach is a sentence level. So that is, we want to create paraphrases of the entire sentence, and the idea is to use the technique called back translation, right? So to use back translation, for example, if we have an input sentence X in English, we can use English to German model to translate it to German, and this is the output as Y. Then we use the other direction, right? So we take a German to English translation model and translate Y back to English, right? So in this output will be X prime, right? So the assumption here is that both translation models are really good. So the output X prime will have the same meaning as the input X, but the sentence will look different, right? So that is why we can create a paraphrase of the original sentence X. So this is a sentence level data augmentation strategy, right? So because here we generate a paraphrase sentence from the original input. And if we have other machine translation models, we can create more paraphrases. Okay, so in addition to text-based augmentation, there are also several other ways to do augmentation in embedding space, right? So for example, in CSE, which is contrastive learning for sentence embeddings, the author proposed to use dropout as a data augmentation method, right? So dropout is the method to help us prevent overfitting, but here the author used that as a way to do data augmentation in embedding space, right? So basically, if this is our input, we can encode the input sentence using the encoder. And then they apply two different, job masks on the output hidden states, right? So in this way, they can create two different embeddings for the same sentence, and they can form a positive pairs, right? So the negative pair will coming from other examples in the same batch. So basically in batch negatives. Okay, so that is a job out. It is originally used for prevent overfitting, but here they can be used. This can be used for data mutation as well. Similarly, Shen et al. In 2020 proposed a simple but effective data augmentation called cutoff, right? So cutoff is actually a structured version of dropout, right? So because here, as you can see, if we have a sentence, we can view this sentence as a L by D matrix, right? So where L is the number of tokens and a D is the dimension of word embeddings. In this way, they can apply token cutoff to remove some rows corresponding to some tokens, or they can apply feature cutoff to remove some columns corresponding to some features, or they can do span cutoff to remove the entire text spans, right? So that is cutoff. And mix-up is another data augmentation idea in embedding space. Right, so that is, we want to do some, if we have two samples, we can do some interpolation over this pair to create another sample, right? So that is mix-up idea, right? So formally, if you consider a pair of label samples, BI, YI, and BJ, YJ, then you can perform linear interpolation using lambda and 1 minus lambda over both the embeddings and also the labels to create a new sample, BIJ and YIJ, right? So this gives you a new sample, right? So that is mix-up. Okay, so finally, we want to briefly mention the third data augmentation method, which is basically to do manual augmentation, right? So this is most useful if you want to have some non-trivial but really diverse augmentation that can truly reflect human usage of language, right? So for example, NAACL Augmenter is a recent effort of crowdsourcing wisdom of researchers to do augmentation on many NLP texts, right? So they have 117 ways of doing data augmentation, and you can use them directly or contribute to their repo as shown in this link, right? So that is manual data augmentation example. Okay, so that basically for the data augmentation for text, and that is the first challenge of self-supervised learning, right? So that is how can we do some data augmentation, which is non-trivial changes, but do not, really change the semantic meaning, right? So that is the first challenge of contrast data in, self-supervised learning. Okay, so the next challenge is, as you can remember, if you remember, is the sampling bias. So what is sampling bias? So in self-supervised setting, we don't know the label of the data set, right? So we start from the anchor point X and do some data augmentation to get positive pair. And then for the negative pair, we're going to use some random sampling. Such random sampling procedure is somewhat not very accurate because it can accidentally get some samples that should be positive, right? So that is the risk of sampling bias, right? So such false negative sample issue is called sampling bias. So in this paper from Chong et al. In 2020, they showed that the sampling bias really hurts the performance, as shown in this green figure, right? So if we know the label of those false negative samples and remove them from training, then the unbiased training will be much better, as shown in this blue figure. Okay, so how we can do better? So Chong et al. Then proposed an algorithm of debiased contrastive learning. The key idea is that we can assume a prior probability between positive and negative, and then approximate the distribution of negative samples to debias the loss, right? So basically, we assume our sampling distribution P is here, and it is a combination of both positive distribution plus and also the negative distribution P minus, right? So, and we have a prior probability tau plus and tau minus. And here, if you think about this, we do know P, right? So because we can sample, and we can also, we also know P plus, right? Because we can create positive pairs by ourselves, but we don't really know P minus, right? So therefore, we can do something like this. We can first sample n samples, right? So we first have n samples from the P distribution, right? So in this case, it contains both positive and negative. Then we can get another m positive samples, right? So that is, we can sample m samples from the P plus distribution, right? So given this, we can rearrange this term so that we can write P minus as P minus P plus divided by this tau minus, right? So in this way, we can estimate the distribution of P minus and replace it, place it in our contrastive objective function, especially in this denominator, right? So that is a algorithm of debiased contrastive learning. Okay, so that is the second challenge of self-supervised learning. And the third challenge is hard negative netting. So what is that? What is hard negative? As this figure shows, suppose A is our anchor point, and P is some positive example. And N, like N1, N2, and N3, they are all negative samples, right? So our contrast learning objective is that we want to have distance of AN to be greater than the distance of AP, at least by the margin, right? So this is our margin. Right? So as you can see, if the negative is outside of this dashed circle, they already satisfy this criteria, right? So basically N3 is easy negative. So furthermore, if the negative is inside the dashed circle, but still far enough, then the positive pair, they are semi-hard negative, right? So in this case, N2 is semi-negative. But if the negative is inside the solid circle line, such as N1, so basically they are even closer than the positive, then it is a negative, hard negative sample, right? So in this case, N1 is the hard negative example. So finding hard negatives is very important to make contrast learning effective, because from the hard negative, we can have better learning signals. Okay, so how can we do hard negative nettings in our case? In Robinson et al. 2021, they proposed a strategy called impulse sampling for hard negative mining, right? So the key idea is that if the negative sample is close to the anchor point, then we should upweight its probability of being selected. right? To do this, we can compute the distance between anchor point and all the other negative samples. And then we can modify the sampling, original sampling probability to reflect this important sampling criteria, right? So then the new sampling probability, we can multiply it by the exponential of the similarity, right? So in this way, we can upweight the negative sample if it is really close to our anchor point, right? So that is hard negative mining by importance sampling. Okay, furthermore, we can also consider so-called hard positive mining, right? So this is somewhat different from hard negative mining, but it's also a similar idea, but on the other side, right? So Kim et al. In 2020 showed that it is also effective to do not only hard negative, but also hard positive mining, right? So they can create basically using adversarial examples that are positive, but confuses the model, right? So then they can show that using this hard positive, if they use this example in their contrastive learning, they can improve robustness of the model, right? So that is hard positive mining. Okay, so that is basically the third challenge, right? So, and then we're going to the fourth challenge, which is in order to have good performance, contrastive learning often requires very large batch size, right? For example, ECM, CLIR, and CLIP. So I'm quoting their papers, and both of the papers, they report that they train the model with very large batch size, up to 32,000, right? So this is especially true when we use in-batch negatives, right? So if we have this is because if we have a large batch size and we are using in-batch negatives, then there are more examples to do contrast, right? So, and we can cover more diverse negative examples to provide meaningful learning signals to have good representations, right? So as you can see from the figure, up to 32,000 batch size, we can still see really good good performance in SIM-CLIR, right? So that is a fourth challenge of large batch size. If we are going to use large batch size, the memory requirement and computation cost will be a concern, right? So, and to deal with this, here we introduce two solutions. The first solution is called memory bank. We can reduce computation by memory bank. So the idea is we can compute and store all the representations in advance, and this is our memory bank. And if we need some of those, we're going to directly get those instead of computing them on fly, right? So that is the idea, right? So Wu et al. Proposed this idea of memory bank, and they use this in their contrast learning paper for images. So that is our first idea. We can pre-compute and store all the representations, and this is our memory bank. The second solution is momentum contrast, or people call this MoCo, proposed by He et al. In 2020. Right? So they first noticed that contrast learning is essentially learning to match a query to a key, right? So that is essentially what contrast learning does. If you think about traditional contrast learning framework, they use an encoder for the query and a decoder for the key, and do backpropagation through both sides, right? So however, in this way, the number of negative samples is actually restricted to the size of the mini batch, right? So that is why we need very large batch size. By contrast, He et al. propose to use a momentum encoder for the key, and they can maintain a queue of keys. And the key encoder is updated using momentum, right? So in this way, we can scale the number of negative samples, right? So because basically we're trying to use momentum to keep track of a queue of keys to incorporate many keys at one time, right? So in this way, we can make sure our contrastive learning training is more stable because we're trying to maintain a large and consistent dictionary. So this gives us better performance for contrastive learning, right? So that is the second solution, using momentum contrast to scale the number of negative examples. Okay, so basically we talked about 4 challenges of self-supervised contrastive learning. So as you can see, most contrast learning frameworks are still self-supervised. So, so that is why we have those 4 challenges. But there is also another alternative that is self-supervised contrast learning, right? So it's supervised contrast learning. So in supervised contrast learning, we can directly use data labels to get positive pairs and negative pairs. So that is, we already know those images are all dogs and those images are all cats. So in this way, we don't have, for example, the risk of sampling bias, right? Because we can make sure they are really positive pairs and the real negative pairs. Okay, so basically in supervised contrastive learning, positive pairs are just from the same class, while negative pairs are from a different class, right? So in this way, there are several advantages, right? So we don't really need to do very hard data augmentation strategies, and there is no risk of sampling bias or false negative, and there is no need to have very large batch size, right? So in practice, we know the labels, probably we don't need to have so many contrastive pairs. But all of these advantages is based on the fact that we do have the label data, right? So that is the disadvantage of this strategy, right? So of this framework. Actually, there are already many successful examples to use contrastive learning in supervised fashion, such as SentenceBird, SimCSE. So SentenceBird is trying to model a pair of, also model the sentence embedding from the bird. And SimCSE, as we introduced before, they have unsupervised version, but we're going to look at supervised version as well. So DPR, dense passage retrieval, they can build good representation from the passage for information retrieval and question answering tasks, and also CLIP, we're going to talk about that as well, is the multimodal representation of text and images, right? So they are successful examples to use contrastive learning using some supervision from the data. Okay, so for example, in SimCLC, they use natural language inference data set for supervision, right? So in unsupervised version, they use dropout, right? But they can also have a supervised version. So that is, for the positive pair, they can use entailment pairs from ALI datasets. And for the negative pair, they can use contradiction ALI pairs plus some in-batch negatives, right? So they compare their supervised version and unsupervised version and found that this supervised version works better. Okay, so another example of supervised contrastive learning is CLIP, right? So in this case, they use image captions, labeled image captions as their supervision. right? So they use this to learn multimodal representation of text and images. Basically, if you have a batch of n, image and caption pairs, then the positive will be n correct image caption pairs, and then you can formulate other pairs as negative, right? So this is their learning strategy for CLIP. Okay, so that is our second part, right? So in this part, we cover the issues of contrastive data sampling and augmentation strategies, right? So we investigate first 4 challenges of self-supervised contrast learning, and then we introduce some solutions for each, right? So for data augmentation, we talk about 4 different ways to do data augmentation. And we also talk about sampling bias and how to do debiased contrast learning. And for hard negative mining, we also introduced the idea of important sampling and also reversal examples. And finally, to deal with large batch size, we can have either memory bank or momentum encoder. So that is the 4 challenges. And also we talk about supervised contrastive learning as another alternative to use. They can use label data set for contrastive signals. Okay, so that is our part 2. Okay, so to move on, the third part is the analysis of contrastive learning. Hopefully at this point, from the first 2 parts, you already know how we can create contrastive data and apply contrastive learning objectives, right? So that is first 2 parts. In this third part, we're going to look at some interesting analysis work to help us understand when and how contrastive learning can work, right? So especially, we are going to talk about 4 aspects, right? So the first, we're going to provide some geometric interpretation. And later, we're going to talk about the connection between contrastive learning and also mutual information. And third, we're going to briefly talk about some theoretical analysis work to help us, maybe some have provable guarantee about when contrastive learning can work. And also finally, we're going to briefly talk about robustness and security issue of contrastive learning. Okay, so if contrast learning is creating an embedding space, what would the space look like, right? So to answer this question, Wang and Isola in 2020, they studied the embedding space of contrast learning as a hypersphere, right? So basically a hypersphere is a unit sphere of the n-dimensional space. And all the embeddings are normalized, so there are some points on this hypersphere, right? So that is their interpretation of this contrast learning space. And then they can, using this, they can explain the success of contrast learning in 2 key properties in loss function, right? So the first property is the alignment of features from positive pairs, right? So therefore, if you have 2 pairs that are similar, then they should have very close positions on this hypersphere, right? So that is the so-called alignment, force, right? So you're going to force similar samples to have similar features, to have close positions of this hypersphere. The second is uniformity of features coming from negative pairs, right? So that is, if you look at all possible classes, all possible embeddings, they should be distributed uniformly and they are spread out on this hypersphere, right? So this is actually achieved if we want to, make sure the negative pairs stay far apart, right? So if we are going to optimize that term, then that term will give us this uniformity to preserve maximal information, right? So that is two key properties in this paper to understand, contrast learning in this geometric, interpretation. Okay, so the premise interpretation from Wang and NAACL in 2020, it is for self-supervised, contrast learning, right? So, and now if we have supervised contrast learning, so that is if we do know the class labels, all the classes and all the labels for all the images, then we can, have a stronger, scenario. So in this paper from Graf et al. In 2021, they further showed that in this case of supervised contrast learning, eventually it will converge to the class collapse, right? So, and everything will be collapsed to this singular, a regular simplex. So this means every point from the same class, right? So if there are two dogs and they are from same class, then they were going to have the same embedding of the same point as this, right? So if you have another class, it will be another vertex in this simplex, right? So basically all the class points will form this simplex so that they are separated as much as possible on this hypersphere. Okay, so that is, if you have supervised contrast learning, it will collapse to this singular regular simplex. Okay, so that is our, geometric interpretation. And the second is mutual information. So another way to understand contrast learning is by understanding its connection to mutual information. So what is mutual information? So a review of mutual information is here, right? So mutual information between two random variables is defined in this equation, right? So if you have two random variables, x and x plus, for example, x is our anchor point, x plus is the positive sample, and then this is the mutual information of that, right? So it is the KL divergence between their joint distribution and the product of their marginal distributions, right? So the mutual information between two random variables is going to measure how dependent they are on the other one, right? So that is why we are going to measure the KL divergence here. If two random variables are independent, so that means P of x plus is equal to P of x times P of x plus, right? So that is they're independent, then their mutual information will be zero, right? So when we say we want to maximize mutual information, so that means we want to make them as dependent as possible, right? So on the contrary, if we minimize mutual information, we will make them as independent as possible. Okay, so now we understand what is mutual information, but how does that relate to contrastive learning? So to understand this, let's go back to the info NCE laws, right? So recall that info NCE uses softmax laws to differentiate a positive sample from a set of noise examples, right? So C here is the embedding of our anchor point. And we have n samples, including one positive samples and n minus one negative samples, right? So then we're going to pick this one positive samples correctly, right? And this is the goal of info NCE. So how does we do this, right? So we measure the probability as follows, right? So in the numerator, we have the probability mass that xi is the positive and every other is negative, right? So that means xi is from this distribution weak here, but all the other examples are from the original distribution, right? So that is our numerator. And in the denominator, we're going to sum over all possible cases, right? So we're going to say, okay, probably we're going to have the first is the positive and the remaining one is negative. And then the second is positive and the remaining one is negative. And we're going to sum over all possible cases, right? So that is the denominator. And if we're going to take this division, then we're going to have the probability of our model correctly pick out these correct examples, right, of I, right? So this is our original info NCE setting. Okay, so so now we have this equation, and then we can do some simplification, and especially for the numerator, we have this, right? So if you multiply p of xi here, then you can have something like this, right? So you can simplify everything a little bit, and in the numerator, we're going to have p of xi given c divided by p of xi, right? And in the denominator, we're going to sum over all possible other cases as well. Then, as you can see, the key term is this, right? So p of x given c divided by p of x, right? So this term is actually proportional to the mutual information between x and c, right? So that's the connection. So basically, by working through this info NCE laws, we end up with this mutual information term, right? So we end up with modeling their mutual information between x and c, right? Between the positive example and the anchor point. So therefore, we can use a scoring function f of x comma c, which is proportional to this mutual information. And the loss becomes this format, which is more familiar to us, right? So that is the connection between info NCE and mutual information. So to sum up, so info NCE, which is probably the most popular contrastive learning objective, is essentially maximizing mutual information of positive pairs while minimizing mutual information of negative pairs, right? So that is the connection. Okay, so as a direct application of this, here is a paper called Info Sentence BERT. They use this idea of maximizing mutual information to train sentence embeddings by using this framework, right? So basically, if they have a sentence, they will feed this sentence to BERT, get some embeddings from the BERT, and then use convolutional neural networks to create global representation and local representation, right? So for example, the global representation could be pulling of all the convolutional outputs, but local representation will be looking at some chunk of the text, right? So then they can create global representations and local representations. Then they maximize the mutual information between local representation and global representation of the same sentence. And also, they can have another sentence doing the same thing, but they can minimize the mutual information from the different sentences, right? So if you know InfoMax, so this is very similar to InfoMax if you know about it. Oops. Okay, so that is the connection between contrastive learning and mutual information, right? So if you're going to do contrast learning, it is actually doing something similar to maximizing mutual information for positive pairs. Okay, furthermore, mutual information can also get us to do contrastive data selection. So what does that mean? So one of the key questions in contrastive learning is that if we don't have annotated labels available, how can we select the views to which the representation should be invariant, right? So in other words, what pairs should be our positive pairs for contrastive learning? To answer this question, in this paper from Google, they proposed this info mean hypothesis. So that is the views that yield the best results should discard as much information in the input as possible, except for the task relevant information, such as the label of the object. So therefore, that means we should make the positive pairs to be as different as possible. And this can be achieved by minimizing their mutual information. Right? So in other words, you should pick the positive pairs with minimal mutual information and let the model to maximize their representation to have maximal mutual information, right? So in other words, we're going to learn by maximizing mutual information, and we're going to select data by minimizing mutual information. Okay, so that is the connection between contrastive learning and mutual information. And the next is about some theoretical analysis. Actually, while contrastive learning is very successful in practice, there are not so much work on theoretical analysis for contrastive learning. So one of early efforts is from Aurora et al. In 2019, and they propose a theoretical framework to draw connection between semantic similarity in contrastive learning and the membership in the same latent class, right? So this can explain why unlabeled data can benefit downstream supervised tasks, right? So based on this framework, they go on to provide a provable guarantee on the performance of the learned representations. They show that the unsupervised loss is a surrogate for the average supervised loss, right? So that is one of the early analysis work for contrastive learning. Another interesting work is from Haochen et al. In 2021. What is interesting about this is that they use graph as a representation of contrastive learning data. To be specific, they first propose a population augmentation graph, right? So two augmented data are connected if they are views of the same natural data point. As you can see from this left figure, in this way, we can have a very nice organization of subclasses using subgraphs. Right? So later on this graph, they can propose spectral contrastive loss, right? So they connect contrastive learning to spectral decomposition on the adjacent matrix of the graph, right? So that is a second interesting application, theoretical analysis of contrastive learning. And last, I want to mention a little bit about robustness and security concern of contrastive learning models. In this paper by Carlini and Terzis, they ask the question, can we trust contrastive learning models like CLIP, which is trained on noisy and curated training data sets? To answer this question, they propose two attacking methods, right? So, and they found that these contrastive learning models are very vulnerable, right? So they are not very robust. So to be specific, in the first method, target poisoning, the attacking goal is to misclassify a particular testable input to a target label. So they found that they can only poison 0.0001% of the data set to have a very high probability of successful attack. And in the second method, backdoor attack, the attack goal is a bit harder, right? So they want to misclassify any image during testing time by overlaying a small patch on the image, right? So it turns out they can also do this by poisoning 0.01% of a data set. So that means if you have a 3 million sample in your training data, they can only manipulate 300 images to achieve this goal. Right, so, okay, so that's basically concludes the first part of this tutorial. So we cover different contrastive learning objectives, and we also cover different, contrastive data sampling and augmentation strategies. And finally, we look through several papers to help us understand when and how contrast learning can work.
Hello, this is Yongfeng Ji. I'm an assistant professor at University of Virginia. I'm going to talk about the second part, contrastive learning for natural language processing. It is not a surprise. There's many publications. As explained in the first part, the number of the publications keep increasing every year. So it's going to be a challenge to summarize this work without running to the risk of being, just a list of papers. So what I'm going to do here is I'm start from this outline here. Just basically explain the structure of this part. So sort of give you an expectation of what you're going to see in the following slides. So the basic idea to organize this section is there are 3 perspectives we can look into those publications. The commonality is they all use contrastive learning. And the other commonality is, of course, we're focused on application on natural language processing. But if we look into the first perspective, which is going to be the NLP research topic, and we can pretty much find contrastive learning has been used in, basically all the NLP topics, if we're thinking from the high level. For example, it's being used in pre-training and representation learning. We use the text and classification task, all kinds of classification, not just text classification. They're being used in the reasoning task, which covers question answer and common sense knowledge and reasoning. It's being used in the generation task, and here we define the generation task in the broader sense, which covers not just text generation, but also summarization and machine translation. That's the first perspective. And the second perspective is the design choice. The first part, we'll talk about the general idea of contrastive learning. So for a particular application, there's at least 2 questions which I think we should look into for each work. And those 2 questions all belongs to the design choice. The first question is how to construct the additional example, those contrastive examples or contrastive sample. So I call it sample construction. And the second question is learning. So once we have those contrastive example, how we integrate that into learning, incorporate that into the learning pursuit. So my understanding is each of the work need to answer these 2 questions, whether it's using some existing algorithm or come up some new idea. So those are the 2 questions. we should look into. And the third perspective is sort of, step back and looking at those whole contrastive learning for natural language processing from the very high level and trying to understand what benefit, what advantage contrastive learning can offer to natural language processing tasks. So the way we organize the second part is we're going to use the NLP rich topic, which shows task, as the first level of selection. And the second level, for each work, we're going to answer two questions, which is the design choice, and how to construct the contrastive sample, and how to integrate this into learning. And then the second part of the second component of this part, so we're going to talk about the advantage, the value, or the benefit of contrastive learning individually. And one thing I would like to highlight is because the importance of the interpretability and robustness, so we isolate that into an individual part, and my colleague will talk about that after my presentation. Okay, so let's take a close look at the first two perspectives. First of all, like I said, there are many applications in natural language processing which has been touched on those ideas as contrastive learning ideas. And we summarized into, on the high level, summarize this into 4 categories. The first category is classification, which covers text classification, information extraction, and some of the vision and language tasks. So within this category, we're going to focus on text classification just as an example to introduce some representative work. And the second dimension is reasoning. So I realized there may be a different opinion about which task fall into which category. For example, some of the vision and language task actually belongs to the reasoning category. But anyway, the basic idea is to sort of summarize those work using just one option, and this is not actually going to have a significant. This categorization won't have a significant impact in the following slides, as you're going to see. With the second category, we're going to talk about some example work from question answering. For text, for the generation category, we're going to focus on text generation, and there's some summarization tasks we're going to touch upon later. And for the pre-training and the representation learning, it's not going to be a surprise. We can just focus on the pre-training strategy, how contrastive learning can be used for pre-training. Okay, so as I said, regardless what type of application, which category we pick, there are 2 common questions we need, each work trying to answer. Of course, for each individual paper, there are many other technical details, but we just focus on the information related to contrastive learning. And from this angle, there are 2 common questions or 2 key questions each paper need to answer. The first question is how to construct contrastive example or contrastive sample. As we're going to see in the following slides, those methods is going, those methods include role-based method. If we know how to take an original training example, sort of modified based on some handcrafted roles. And we can also use some existing text generation platform to generate, based on the original example, to generate some new example. In particular, along this line, where I think back translation is one of the popular methods being used. You translate the original example to another language and translate back. for some other tasks like text generation, question answer, which requires there's alignment between two chunk of text, and one way to create, for example, negative sample is to shuffle the alignment. You pick a question from associated with a different passage and attach to another passage, which create a negative example, contrastive example. So all those four components are focused on the text level, which is something we can see individual, either modifying the individual word or generates the completely new text. And another way of generating this contrastive example is sort of not directly visible, or it's more like implicit way of construct those contrastive example is to operating in the latent space. So we're going to talk about one of the example, at least one of the example in the following slides. Now those are the representative method of construct contrastive example. After we have this contrastive example, the way of using those example in learning typically are three approaches. The first approach, well, it's not exactly a non-overlapping categorization. So I guess this is more like a highlight. The highlights the difference of how to use those examples. The first typical approach is to use those contrastive example and together with existing training objectives. Like if you're working on classification problem, then that is going to be the cross-entropy loss. And you have this new example, which also you can use the cross-entropy loss, just combine them together, do a joint optimization. The second approach mainly focus on the construct the new loss function. That is usually more like an auxiliary task or some other relevant things where you have those example, but you're not going to use the example directly, training directly with the task you entered, for example, classification, instead of you doing some auxiliary task. For example, when you have this constructed pseudo example and you have the original example, one thing you can do is to train to build auxiliary task and ask the model to predict whether this is original example from the training set or is the example you constructed, from the simple construction, from the first question, the answer of the first question. So those are usually involve designing a new constructive loss. And of course, there is some other constructive loss which involves, whether you're going to differentiate those example or some other related things. So we're going to talk about particularly the reweighting contrastive example as one of the representative work in the following. Before I start to talk about the detail, just make sure we're on the same page. So here's what I'm going to do in the, for each work selected. So we're going to select the work using some example NLP task like text classification, text generation. And for each work, we're going to talk about the task, the focus of the task in this work, and particularly the design choice involves the two questions explained in the previous slides. And there's an individual like a subsection where we're going to summarize the four advantages. So the presentation format, as something you're going to expect in the following, is we're going to mainly focus on answering the two questions: simple construction and as the learning strategy. So again, I would like to reiterate my my opinion. So the way we select those work is by no means comprehensive, and even I probably shouldn't use the word representative. It's just some example work we're familiar, and we're trying to maximize the coverage in terms of those methods regarding those two questions. And we realized there's many other interesting work we didn't cover in this part of the tutorial. So if you have any comments or opinion about how we can organize those material in the future and make it, getting a better organization of this material, so any comments is welcomed. Thank you. Okay, so let's get started. The first NLP task we would like to talk about is the classification. As the first method, which is also a method being popularly used in the NLP domain, it's called cutoff. So the basic idea of this method is inspired by the multi-view learning, which is a classical idea invented many years ago. The basic idea is assume, for a classification task, assume the information in the input is redundant. And you can actually, based on the original input to construct a different view of the data. The original paper is talking about web page, and they argue about both the content and the hyperlink in the web page can provide enough information for a classification task. So the cutoff idea is sort of similar from this perspective. The argument is when the input is redundant and we can sort of cut something off, and that will give a way to create some new pseudo example. And because the assumption the information is redundant, and we should assume this newly constructed example also being able to make a similar or the same prediction. So again, it goes back to the two questions we asked, how to construct the example, how to do training. And this cutoff idea merely focuses on the sample construction. In particular, in the work, they offer 3 different ways to construct the cutoff. The first way is if we're going to use this example, if we use this figure as an example, each row here corresponding, so this is, first of all, this is the word embedding matrix. Each row here is one word or token. Each column here is the one dimension of the word embedding, or you can consider this the feature. So the straightforward way, the way of doing cutoff is you can do both directions. In the first cutoff strategy, is the token cutoff, is you can remove each row of this word embedding matrix. And for the feature cutoff, you can remove each column of this feature of this embedding matrix. And of course, there's a special case of the token cutoff called the span cutoff, where you cut 2 adjacent or more than 2 adjacent words, the embedding, associated embedding, cut it off from this embedding matrix. So those are the 3 operations to construct those examples. And once we have those examples, and this goes to the we get to answer the second question: how are we going to do learning? How are we going to do training? It turns out the training strategy. Part of the training strategy is very similar to what we already know, like we talk about in the multi-view learning. For example, when you have an original example X and the label Y, this is the standard training strategy where you have the cross entropy loss. And from the multi-view learning, we also need to construct additional component in the object function, which is for each pseudo example constructed by the cutoff, we expect this pseudo example also being able to make the same prediction. So that's the basic assumption of multi-view learning. But there's also additional strategy, which just to make sure the similarity or the prediction similarity between the original example and all the constructed example. So this is particularly defined by the Jackson-Shannon divergence, which is you have n different prediction probability plus the original prediction probability. You just take the average, which is going to be this term, and then for each prediction, individual prediction probability, you compute the KL divergence. So this is the generalized version. Usually we see the Jackson-Shannon divergence as two prediction probability, as two probabilities, sorry. But this is the generalized version where we have n+1 different prediction probability, where you compute the KL divergence between each of the individual probability with the average probability. So that's the basic idea, to make sure the prediction probability are similar. Add them together, that give us this entire loss function, and optimize this loss function will do the learning. So as you can see, we're going to follow pretty much the similar structure to introduce each new work. Particular is the sample construction and learning. Okay, so there's something intuitive I would like to offer, which is also the example I got from the paper. So first of all, there are three different cutoff operations, but we notice in the later in other work of doing contrastive learning, the span cutoff being the one used based on my observation is being used in many other works, and so I would like to give this I would like to give this one some special attention. So the intuition of the span cutoff is you cut a chunk of text out, but still the assumption is once you left those text chunk off, the new example should have the same label as the original example. For a sentiment classification task, we have the original input, and there are three different ways to cut a span, which basically cut off the individual span, the first one, the second one, and the third one. And the assumption is once we do that, we're going to assume they have the same sentiment, which goes back to the training objective. So for every cutoff example, we use the original label. Now, by looking at those examples, there's maybe maybe a different opinion about whether we should think about they have the same label. Particularly what I noticed for the second case, where you cut the word happy, which should be considered as a sentiment keyword. But anyway, so I just want to give you some intuition about how those examples being constructed, and how this can be used in the contrastive learning. And there's another relevant idea. There's another relevant idea in this case, which is dropout. And as mentioned in this paper, the difference between dropout and cutoff is more like a structure way to drop some information out. Like particularly in this case, the span drop, which is vanilla dropout probably cannot do that, because the basic idea of dropout is you treat this matrix and randomly drop some cell of this matrix. without additional constraint, the vanilla dropout cannot do the same effect as this cutoff. But this is also a reminder about using dropout as a data augmentation method, which is has been studied also in many other work of the contrastive learning. So the second work I would like to explain here is the contrastive self-supervised encoder representation from transformer. It's called the CERT for short. So the basic idea, as illustrated on the figure on the right, is a pipeline. So this work proposed a contrastive learning strategy to do pre-training. So it started from the basic pre-training, which is we're already familiar with the BERT pre-training, and then there is a middle component. Before we get into fine-tuning, there's a middle component which is called the CSSL pre-training, which is called the contrastive self-supervised learning. The basic idea is for this pre-training, we're going to use the tags from the target task. For example, assume you're doing a task from the glue benchmark. You have the tags from the target task. And this pre-training idea is to use particularly the tags from the target task, and to do the pre-training before the fine-tuning. And the basic idea of this middle layer pre-training is to use back translation to construct some example, the similar example. Well, particularly in this case, they use English to German or English to Chinese translation. And the training strategy is a common strategy called the momentum contrastive learning, which will be explained in the first part. So the idea of this pre-training is it constructed an auxiliary task where this auxiliary task will take the output from the pre-training to predict whether two augmented data are from the original example or not. So this is something related to what we have explained in the previous. Instead of directly incorporate this into the target task or the target objective function we're going to use, you can also construct auxiliary task. And one typical way of construct this auxiliary task is to predict whether the text is from the original training set, or it's a pseudo example constructed later. So another task we would like to introduce here is also aligned with the momentum contrastive learning. The basic idea is instead of just using one simple construction strategy, let's just use multiple of them. In the previous, the first part, and also the beginning of this part, we talk about the cutoff, back translation, which is the previous idea, and there's some other idea like mixed up. So you can think about the data augmentation strategy. Well, I think this work strategically can use any data augmentation strategy, but particularly in this work, they use 5 different, which I'm going to explain in the next page. So once you have those data augmentation strategy, you can stack them together, one after another, begin to construct multiple examples. And the basic idea as contrastive learning is you're going to train this model and to differentiate whether this is the example augmented from the original sample or it's some other example, some contrastive example. So the basic idea of doing training is following this momentum contrastive learning with a memory bank, particularly in this part. And the reason is by having this memory bank, you sort of saving some effort of compute the representation of this of those contrastive example. So the based on my understanding, the part which I think, at least to me, is very interesting is they have the idea of sample construction where you can stack all these different data augmentation strategy together and to sort of find which combination gives you the best. In the paper, they're talking about lots of the results, but I just want to highlight one of them, which they have the conclusion of saying there are two particular components stacked together gives the best performance, which is back translation and adversarial example. Well, I think I should say adversarial example generation. So as you can see from this table, even the simple augmentation strategy, augmentation strategy outperform the original baseline, which is the Roberta base, which shows the advantage can offer by doing this contrastive learning. But of course, if you find the right combination, and the performance can get even better. So if you want to know the performance of different combination of detail and some interesting discussion, I would suggest to take a look at this paper. And we talk so far. We talk about the different sample construction strategy, and also the last page we talk about we can stack those data augmentation strategies together. Just combine them together. That's a new strategy. But there's a different question we're trying to answer in this paper is when we have those samples, those examples. The simple way we can construct a sample is to for the classification task, we can run the sample example from the original training set and treat that as an active example. So this is actually being used also a lot in the contrastive learning, and specifically if you have a mini batch, and you can sample within this mini batch, the example from a different label, and treat that as an active example. If you can also sample within this mini batch example with the same label and treat that as a positive example. So that's the basic idea of this. That's the starting point of this work doing the sample construction. We use the existing positive and negative example in the mini batch, and depends on whether associated with the same label or not, being categorized as the positive sample or negative sample. By the way, I often find this is confusing because, for example, if we're working on a classification task, the label itself is called the positive or negative. But here, the positive and negative example is regarding the, we have a target sample, and the target sample have a label. If we got another sample which have the same label, I will consider it as a positive. And if we get another sample which has a different label, we consider it as negative. So just be careful. The word positive and negative got overload in this discussion. Okay, so the sample construction in this work is simple, but the idea is very interesting in this work regarding where they argue about in a different example should have the different weight. And particularly they propose something called a weighted label aware constructive loss. And the basic idea of designing this loss is if we get rid of those weights, for example, get rid of those weights, and I think we pretty much recognize this the standard contrastive loss, one typical way of using of doing contrastive learning, where you have a positive example where you sample from somewhere and construct this is the positive site, but for when you do the comparison between the original example and the positive example, you also sample within the mini batch and treat those as a negative example. So those are the typical contrastive loss. And the new thing in this work is to introduce those weights. And depends on the label, and those weights are going to be different. So let's take a look on the figure on the right. The basic pipeline of this work is we have these two existing cross entropy laws, and also by design there's a weighting network which outputs a vector which has the same dimension as the number of the classes. So basically, for any given example, each class will have a one number associated as a weight. Of course, it's being normalized. And to train this weighting network, we need another cross entropy loss. So what's in the middle here is the proposed weighted constructive loss, where for each label, this WI, particularly designed for this training example I, and for each label, it gives a weight. So this idea is it gives the different, for one particular example, it gives different label a different weight. And this weighted example, as argued by this work, should work better than the original contrastive loss, where you just treat those or get rid of this or treat those each W as one. Okay, so that's pretty much what I would like to introduce about the contrastive learning for text classification. If you think about it, this is besides the task applied, most of the strategy we explained in the previous slides are pretty much general or generic, can be used in many other NLP tasks, and which is also one of the purpose of this tutorial. So we noticed there's many interesting work. Although when they propose the work, of course they have to use a specific NLP application to demonstrate the benefit of this contrastive learning strategy. But honestly, most of the work can actually be generalized to many other NLP applications. So one of the things you probably realize is during the discussion of the previous slides, I didn't emphasize too much about the specific application. So that's the reason. In the next few slides, we're going to talk about a different application. So the first one is question answer. In this case, the negative example, the sample construction focus on the negative example, which they got the passage, just the passage. If you have the passage and the question pair, you just get the passage. And for a given question, you get a passage from a different passage question pair, and treat that as a negative example. The main focus, one of the main focuses in this work is to address the asymmetric issue between the question and passage pair. So as illustrated in this case, when you have an encoder for the question and have another encoder for the passage, which because this asymmetric asymmetric structure, we cannot just directly use this. I mean, I think you can use, but it's probably not a good performance. Use the original momentum constructive learning. So the solution presented in this work is to present like a symmetric structure, as in this case, you have for each part of the input, you have the question. It gives you two encoders. One is the fast encoder. The second is the slow encoder. So the difference between the fast encoder and the slow encoder is the fast encoder is learning based on the gradient information, while the slow encoder is updated based on the momentum update, which is the same as the previous momentum contrastive learning. So in this case, what this algorithm presents is going to do is for the question, for each of the question loss, we can get the information and use the information to update, the fast encoder, and use the fast encoder to further update the slow encoder. So it's the same thing we can do for the passage encoder set. It's basically the same thing. And the training procedure involves, in order to learn, for example, a good passage encoder, you need to get sort of multiple example on the question set. Well, on the other hand, if you want to learn a good fast encoder, in this case, we need to get multiple negative passage example. So in this case, we're sort of starting from this two loss function and can update symmetrically both the question set and the passage set. To give a further explanation about the difference, the paper present, this is the figure got from the paper. The paper presents just the proposed method as the original momentum contrastive method, just put it together side by side, so you can know the difference. And basically, if you use the vanilla momentum contrastive learning, you have the question and fit into the fast encoder, which is based on the gradient information to learn. And you have the passage and fit into the slow encoder, which use the momentum update. You can get multiple negative example, like the way we get the passage from other questions. I treat it as negative example. We do contrastive learning and use the gradient information to update the faster encoder and use the momentum way to update the slow encoder. So we can do that. But the problem is because this asymmetric issue, we may not get the performances may not good enough. So on the other hand, this model basically double the size. But the good thing is for each question, there is two encoders. One is fast encoder, slow encoder, and for each passage, you also get two encoders. And the updating, as you can see from here, is purely symmetric. For multiple negative example, updates the to update the passage, and get a multiple negative example to update the question. So that's the first method we want to talk about here. The other method about the question answer is the angle of this method is very interesting. They have an argument of saying the bottleneck of contrastive learning is we're not able to easily get the informative negative example. So I think we talk about multiple work, sort of focus on to generate high quality negative example. And this is one of them. And the argument is they sort of double on the claim of saying, if the performance, there's one major bottleneck for contrastive learning is if we do negative sampling within the mini batch, and we may have the problem is not be able to get some informative negative example. And by the way, this work, the original, if we take a look at the original paper, this is not just for question answer. But if you take the application, the experiment, they use question answer as one of the application to demonstrate the potential of this method. So in this case, what they claim, what they propose to do is, you have this retrieval model, or you have, for a given question, you have some candidate answers, and to get the informative negative example, you just need to get from the top of the retrieved document or the retrieved object. The intuition is those, if they're not the correct answer, if they're not the documents you want to retrieve, they got to be the hardest question, the hardest example the model need to learn differentiate. So that's the basic idea. And the training algorithm, they used asynchronized index refresh, which is present in the previous work. So we're not going to talk about the detail here. The other work is also it's still about the question answer, but the setup is different. They're trying to address this question answer problem in the domain adaptation framework, where on one hand, in the source domain, you have all the things you need. You have the context, you have the question, you have the answer. It's basically a supervised task. Well, on the target side, you only have context. From that perspective, it's an unsupervised domain adaptation problem. The way they training a target question answer model is first to use a question generation model, where you have the context from the target domain, and this model will generate both the question and the answer. Both the question and the answer. And yet, then you do joint training. If you want to train the question answer model, which can be used on the target domain, then you do joint training by compare the target question answer pair with the source question answer pair. So basically, what we can do here is to compare both the question, the answer, and the question answer, the cross product from one from the source domain and the other from the target domain. And this is pretty much the intuition here, where you design the loss function based on the the similarity of all the question from the answer from source and target domain, the question from I'm sorry, this is supposed to be the context and the question concatenation. So they compare the context and the question combination from the source and target domain, and compare the cross alignment, the question and the context question, the answer and the context question from one from the source domain, the other from the target domain. And intuitively, we'll understand which one it should be minimized, which one should be maximized. One more thing about this function. Find here is called the feature extractor, and in the neural network, in this paper, to be precise, in this paper, they're using this deep neural network as the feature extractor. You feed the text into the neural network, you'll get dense representation. That's your feature representation. So to get a sort of like a better understanding about this framework, and let's take a look at this nice plot offered by the paper. So there are two information flow. The one information flow, well, to be precise, there are three, but mostly let's just take a look at the first two. With the blue arrow, it indicates the target domain information flow. And the orange color is the source domain information or data flow. So for the source domain, information is pretty clear. You have all the information and you just feed it into this encoder, and you have this answer classifier which tell you the starting ending point of an answer. And of course, the way of training this answer classifier is using cross-entropy loss. But with the target domain, the procedure is a little bit complicated because we need to generate the data first. So this whole thing here is you have the context and fit into a question generation model, generates the synthetic question answer pair. And then this pipeline starting here is very similar. And we do the answer classifier. So the interesting thing is about this part, which is also the 3 components we see at the previous page. So 3 components here. Basically, what I'm trying to do is we compare the answer from both the source and target domain and minimize the discrepancy loss. And you also compare the context question from source and target domain, you minimize it. So the interesting thing is if you get a pair, this context question and answer pair, one from the source domain, the other from the target domain, and this you need to maximize. You need to maximize the discrepancy. So all the 3 things together, interclass loss and negative interclass loss, interclass loss with the cross entropy loss to train this answer classifier. All the 3 things combined together, that's the loss function. Okay, so that's the basic pipeline, which I think, like I mentioned before, those framework, if we have, for example, a nice pseudo data generator, which I think it can be used in some other problem, not just question answer. Okay, so let's jump to another application, text generation. As we have already seen those examples, the major question we need to answer for each work is the sample construction and the training. So for this case, one of the most interesting part of this work, to my understanding, is the way they construct those examples. Those negative example, the way they construct this negative example is to add a small perturbation. And to contrast the positive example, it's add a large perturbation, which is sort of a little bit counterintuitive. But if you combine with the training, and everything just start to make sense. So for the negative example, you add a small perturbation, but during training, you can to minimize the similarity. So the negative example, because the small perturbation looks quite similar to the original example, but you want to maximize. You want to maximize the dissimilarity or minimize the similarity. For the positive example, despite there's a large perturbation, you want to minimize the difference or maximize the similarity. So in this case, you're really pulling together the similar example, despite there may be a difference in their surface form, but you want the model to know, although this is a large perturbation, but it's still, it's a similar example. Well, for the negative case, despite the small perturbation, those are very different. So that's the basic idea, which illustrates, this is also the figure present in the paper, as is trying to pulling the similar example together will push the dissimilar, which is the negative example, far away in the representation space. So another work on text generation, which is contrastive learning. The similarity between this work and the previous work is the both of them handling, the sample construction involves positive and negative example. So the way they construct the negative example is kind of similar to what I've been talking about, either using dropout or using this cutoff. So what they're trying to do is they use just simple dropouts, but they have the different mask, different dropout mask every time. And the point is, for positive example, you fit the original text into a discriminator twice, where every time you use a different dropout mask, it means every time you drop a different part of information, but still tell the model those are two similar examples. On the other hand, for the negative example, just using a pre-trained text generator to generate some random sentence as a negative example. So in this case, you can, the training procedure is basically to improve the robustness of the model. Like, although there's two different dropout, but you still consider similar. On the other hand, for a sentence which is very different, because it's a random sentence, generates random sentence. For an active example, you tell the model those two are very different. So those ideas are, I would say it's intuitive, but also being effective in the text generation literature. So before we end this list of the NLP application, I want to mention another work, which is sort of a standout because the application. We've been talking about this popular application those days. So we've been talking about text classification, and we talk about text generation, and we're also talking about question and answer. Those are the popular applications. But I would like to see, so there's many other NLP applications, which is also very important. So name entity recognition is one of them, which have many potential applications in the real world case. So in this work, the novelty of this work is to use, first of all, to use the representation, word representation, instead of using, for example, the standard point embedding, the user distribution first. And the argument about learning those word embedding as the training objective will consider the word from. So in this case, for example, those two are labeled as the as same NAR label as person. So each of this word is going to be represented as a Gaussian distribution. With during learning, what you want to do is to sort of minimize the difference between those two distributions. Where on the other hand, you're going to maximize the difference between, for example, this word and any other word, which are not, whether it's just the context word or the NAR is an anti-dimension, belongs to a different category. For example, in this case, it belongs to the date category. So in this case, it will bring the benefit of putting the word in the same label, which is similar, having the similar embedding distribution. And this will also offer the advantage when you transfer this model from the source domain to the target domain. Because in that case, when you have the problem in the target domain, and what you need to do is do a very simple, for example, nearest neighbor inference. And the reason this nearest neighbor going to work is because the way you learn this embedding, trying to pull this embedding from the same label close to each other, well, the word embedding distribution to be accurate from a different level far away from each other. So in that case, when you have a very good high quality representation, then you can just use a simple classifier or simple machine learning model to do the inference, which is being demonstrated in this work. In the rest of this part, we can just talk about the advantage of using contrastive learning for natural language processing. Mainly, I'm going to focus on three aspects here: task agnostic representation, fastful text generation, and data efficient learning. The interpretability and explainability will be explained in the next section. So about the syntax representation, one advantage contrastive learning can offer is to address this representation space collapse problem. So as I defined in the previous work, particularly if you look at the representation you got from each layer of this deep neural network model, so as the example shows both BERT and GPT, the common pattern is when you increase the number of layers, you get a deep model, and the similarity of the sentence representations get larger and larger. So in that sense, it means, so just imagine if you have like several hundred dimensions, when you map the sentence representation into this high dimension, and mostly they just very close to each other. So for example, the cosine similarity in the high dimension space with those numbers is not trivial. It's probably trivial in the lower dimension, like you have 2 dimension. So we think about maybe 0.9 as being the craziest one. But 0.6 actually the starting point is not, starting from 0.6, the similarity larger than 0.6 is considered as non-trivial case. So in that sense, how we're able to get informative representation, and mostly, how to effectively utilize the information, effectively utilize this high dimension to encode the information. One thing we've been talking about in the previous slides is this method, which you do further pre-training by using the target data, target tags. Well, the other thing we can do is to come up with directly avoid the representation collapse. The example work, which also been explained in the previous slides, is this SIMC-SE method. The basic idea is you use dropout to create some positive example, and during the training, you try to push the similar example together and push those general representations, randomly retrieve the negative example far away. And in this paper, they also propose there's 2 ways of evaluating the representation space, which is called alignments and uniformity, which in the sense, it shows if you do this contrastive learning, it can help the sentence embedding or the embedding learned from the deep model, just largely distribute in the latent space. There's some other ways to do the pre-training, like you can increase those example, which is, in the original pre-training that we do this mask language model, but there's an alternative way of doing this pre-training, is to consider, instead of just predict the masked word, we replace the word. Replace the word with another word, and the task is, instead of predicting the mask for a given mask to predict where it's come from, instead of doing that, we predict whether they replace the word. So in this case, there are 2 replaced. we predict to replace the word, whether this is the original word or it's a replaced word. So this considered as the alternative way of training, of doing pre-training, and it's been proved empirically, been proved it's effective. And the idea, as I mentioned in the paper, is relevant. It's related to the previous work called the noise contrast estimation, which has been used in natural language processing and many other machine learning tasks. So on top of that, there's another work in doing further pre-training strategy, which is align the different view of the same input against with some unrelated negative example. And this is the sort of can be considered. So if the previous method is considered as the token level, so in this work, this idea can be considered as the sentence level, which is further boosted the representation performance of the neural network. So another dimension of the advantage contrastive learning can offer is on text generation. So as we all know, there's the common problem of text generation is hallucination, which is basically the model is just making up some things or altering the fact. It looks like it's a beautiful coherent sentence, but the information is not accurate. So the issue here is whether the generation text being feasible to the input, or it's whether it contains any factual error. So in this case, we're citing some example from one of the work pointing out this issue, this hallucination issue. Is this different models, they all make this different kind of mistake. Well, the right color is trying to highlight those things which is made up by the generation model. So one way to address this issue, in particular within the application, within the task of text generation, is to do contrastive learning, where we can use the automatic generation text as an active example. So we compare, and this function here, if we just focus on this part, is sort of like a typical contrastive learning objective. Well, on this part, we're going to use some randomly generated text as an active example to do the contrastive learning. The other way to enforce this factual consistent text generation is to use, well, it's particular in these logic to text or semantic parse to text generation problem, where it can perturb this logic form where you get this random logic perturbation, and then using this perturbation to generate some pseudo example, and then use the pseudo example as the comparison. I mean, treat it as an active example to do this constructive learning. So the third dimension here is about is the data efficiency. So consider the case where we do not have enough data to train the model, and this is actually connected with one of the two key questions we trying to answer in the previous slides, which is the sample construction. So naturally, contrastive learning, because it involves the sample construction, it involves using the existing training example efficiently, or it involves some additional strategy, contrast more example. Either way, it can help address the issue where we don't have enough data. So here I just put these two figures, which both of them we have been talked about in the previous slides as an example of sort of data augmentation. So another way of doing data augmentation, as presented in this work here, is it involves some understanding about the problem. For example, if we're trying to do text classification, and on the other hand, if we have a summarization model there, and the idea is, when we get a text and run a summarization model, the model will extract the key information, right? So in addition to accept this key information extracted by the summarization model, all the other word in the original message is being considered as this residual word, which is is probably not related to the classification tag, not related to the core information of the text. But those residual words can actually be used to construct some additional example. For example, if you have another summary, you can mix those residual words. You can combine those residual words with another summary into create a pseudo example of the text, and this text can be considered as a positive sample to another summary. So this is the basic idea of using summarization to create additional example. And this is also, the method itself is called mixture sum, where you get the residual words from another message and got the summary from this message and mix them together.
Now, let's consider using contrast for model interpretability and robustness. Let us first consider contrastive explanation. I quote this question from a seminal paper by Tim. Why did you rob a bank? The robber answered the question, because that is where the money is. This answer can be surprising, because the expected answer should be to the question, why did you rob the bank, rather than obeying the law. So this example illustrates the importance of contrast in question answering. Rather than asking why P, if we ask why P rather than Q, then the question can be more definite. We can also illustrate this by looking at features to represent the question P. Now suppose that we are trying to ask about the concept dog. Without a contrast, in order to define dog, we have a bunch of different features, including head, tail, the fact that it runs, the shape of the head, the shape of the tail, the fact that it has fur, and the barking fact. However, if we ask the question, why this is a dog rather than cat, then the number of necessary features is sharply reduced, and we only need the shape of the head and tail and the barking sound to differentiate the two animals. So this shows the importance of contrast in explanation. It has also been shown in social sciences that humans make explanations by making contrast. Contrastive explanations can also help us to do modeling. This is one example work where the authors make contrastive explanations of model decisions. The current figure shows an example similar to the example earlier. This is for question answering. If the question is, why are they a dentist? Many words from the passage defines the answer. However, if the question asks, why are they a dentist rather than an accountant? then only medical center is the most relevant. If the question is why are they a dentist rather than a surgeon, then both oral and the surgery name might be factors for the differentiation. This is another figure from the paper. You can see that the answers are very different when the question changes from the uncontrast question, why was it decided to hire person X, into the contrastive questions, why was it decided to hire person X rather than not hiring them, or why was it decided to hire person X rather than hiring person Y? In making contrastive explanations, we need to have two things to contrast. One may be the original question. We name it a fact. The other is a contrastive fact. We name it a foil. In question 2, for example, hiring person X is the fact. Not hiring them is the foil. In question 3, hiring person X is the fact, while hiring person Y is the foil. The authors try to create correlations between supporting evidences and the contrast, namely the fact and the foil. Given a pair of fact and foil, we can find a set of supporting contrast by first obtaining a latent contrastive representation in the input space, and then measuring contrastiveness by computing behavior change of the model before and after the projection. Here I leave out the details of the method. Using this method, we can rank different supporting evidences in the input given a pair of fact and foil. And we can also rank different foils given a fact. Here is some results on natural language inference. It has been shown that typical NLI datasets can have artifacts, namely spurious patterns that are not directly related to the causality of the answer. For example, in the table above, there are 3 different types of artifacts, namely the overlap between the hypothesis and the premise, negation in hypothesis, etc. Take overlap, for example. Apparently, this should not directly affect the decision whether the hypothesis is entailed or not. However, in the dataset, more than 60% of the overlapping cases are entailment cases, while that between entailment and contradiction is only 0.006%. This shows some correlation between contrastive explanation and the data artifact. This experiment discusses the supporting evidences given a pair of contrast. Here, the incorrect model prediction is used as a fact, and the gold standard label is used as a foil. In addition, non-contrastive explanation is also labeled by using the non-rows. As can be seen from the figure, contrastive explanations correspond quite well with non-contrastive explanations. In 3 out of the 4 cases, the supporting evidences in the bold row is identical to those in the none row. The authors also did experiments on analyzing social bias using contrastive explanation. The next work we discuss here makes use of contrastive explanations to help common sense reasoning. The motivation is shown in this table. Here, the common sense reasoning task asks the model to fill in the blank. For example, given the sentence, I picked up a bag of peanuts and raisins for a snack. I wanted a sweeter snack out, so I ate the blank for now. The blank should be filled with raisins. And the reason behind is in nature contrastive, because peanuts are salty while raisins tend to be sweet. Given data with only the input and output, the model can be trained end-to-end. However, it doesn't explain its own decision. One way to improve this is self-talk. Given an input, we ask the model to generate the reason why to choose a particular answer and then generates the output. In this paper, the authors investigate a contrastive explanation method. Given an input, the model is asked to give a contrastive explanation and then generate the output. Where does the contrastive explanation come from? The authors asked crowdsourcers to manually label answers, given the input and output. And when they collect statistics, they find that 64 to 76% of the human given answers are in nature contrastive. As a result, the authors extracted templates from the human given explanations that occur more than 10 times and used these templates for generating contrastive explanations. Here, I list some of the example templates. For example, one option happened before or after another option. One option takes longer than another option. Or option 1 likes something while option 2 likes something. Or option 1 is smaller than option 2. Or option 1 is above option 2. Or option 1 can do something while option 2 can do something else. There are also more complicated templates which are extracted in the same way. Now, given an input, the model is supposed to score different templates and answers simultaneously, making use of the auto-filled templates to help better rank answers. Results on different datasets show that by generating contrastive explanations, the model is not only more interpretable, but also gives better scores. Contrast can also be used to evaluate models' robustness, as this paper investigates. So here, the figure shows an example of contrastive data instances. The original example has a figure and a text that matches the figure. However, as shown in the examples below, if we make a small change to the text or the figure itself, the text no longer matches the figure. While this contrast is obvious to the human, it might confuse the model, which is less sensitive to small changes. This figure shows a theory behind. Suppose we have two different types of instances, and the decision boundary to separate these two sets of instances is very complex. However, the training data might be scarce, which makes it apparently easy to separate the two types of examples by using a straight hyperplane. A model that learns to make this decision will face robustness issues. The idea of robustness test is shown in the figure below. We have a few samples of difficult cases, which requires the model to have the complex separating hypersurface to decide correctly. In order to achieve this, the authors manually annotated contrastive test instances for 10 different datasets. The goal is to make the minimum change to the data to flip the output label. The annotation is completely done manually and tested on these 10 different datasets. The human performance does not vary a lot. However, the state-of-the-art models give much lower results on the contrast test set compared with the original test set. This verifies the above hypothesis for model robustness. Here, let me present another paper on sentiment analysis itself. Here, let me present another paper dedicated to the task of sentiment analysis. The authors asked crowdsourcers to make minimum changes to the input to flip the sentiment label. There are several most common categories of edits performed by the crowdsourcers. For example, facts can be changed into what is hoped for, or sarcasm can be suggested. Such modified data is called a revised set in contrast to the original dataset. Results show that models trained on the original dataset can perform very badly on the revised datasets, and vice versa. On the last row, when using both the original data and the revised data to train the model becomes more robust. This gives us a hint that by making augmented data, we might alleviate the issue of weak decision boundaries. Subsequent work also investigated automatic ways to generate counterfactual data. By using the automatically generated counterfactual data, we can also improve the robustness of a model. Let us continue the discussion of robustness. Counterfactuals are small changes of the input that changes the output label. In this table, suppose that the original sentence is shown in the first row. Counterfactual examples are illustrated in the third or last row. When we change unsatisfying to satisfying, the gold label is changed from negative to positive. The work above discusses such cases where the model is insensitive to the change due to incorrect decision boundaries. However, there are also adversarial examples where we change a word in the sentence but the label does not change. For instance, if you look at the second row, when we change ultimately to lastly, the goal output remains negative. But sometimes the model is confused by the change and turns the prediction to a positive label. This is another robustness issue. So if we denote the second row as adversarial ADV and the last row as contrastive or REV, the authors show that models face robustness issues with both cases. In order to address these limitations, the authors automatically mined both adversarial cases and contrastive cases, and designed loss functions to integrate information from both cases. Results show that by considering both robustness issues, the model can give better results on different testing scenarios. Here is another example of adversarial data augmentation. The goal is to address robustness issues when irrelevant words are flipped in the input sentence. In this example, Nolan's films always shock people thanks to his superb directing skills. If we change Nolan's film to Martin's movies, the sentiment label of the sentence should not change because the key rationale lies in the words shock and superb. In order to fix this issue, the authors ask annotators to label the rationale in the decision making. And in this example, the rationale, brain cell killing, and 100% bad are labeled in bold font. Given this labeling, coherent changes to other parts of the sentence should not affect the decision. Patterns other than the rationale, such as the underlined pattern, acting, and plot, should not affect model decision. This paper generates augmented data by automatically giving coherent changes to non-rationale parts of the sentence. And the new data are called semifacts. There are two ways to generate semifacts. The first is a static method, which is shown in the above part of the figure. The second is a dynamic mechanism, which looks at the model decision. It is shown in the bottom part of the figure. Static examples are shown in this table. In the first example, given the word sad, we can make coherent changes to the other part of the sentence while maintaining the sentiment label. Dynamic examples are shown in this figure. Post hoc methods are used to check the model decision. If the model relies on features rather than the rationale to make decision, data augmentation is done by changing the spurious patterns that the model relies on. Using this method, the authors show that by only manually labeling 50 examples with rationale and making data augmentation, the model can give stronger generalization results compared to using thousands of training examples using traditional end-to-end learning. In summary, the key to model robustness is the rationale, or the causal features that the model makes use of. By making contrast, we can evaluate the robustness of models and also perform data augmentation to improve it. Now, let's make a summary. We have discussed the concept of contrastive learning, as well as its application to different NLP issues. In fact, contrast is a very general concept. It has strong social scientific motivations. Contrast has been used frequently in our learning and communications. The boundary between contrastive learning and traditional log likelihood learning. The boundary between contrastive learning objectives and traditional maximum log likelihood objectives can be subtle. Here, let's consider a classification example. Suppose that we have a neural network to turn an input into a hidden representation H, and then we apply a linear layer to calculate the output class probabilities. The parameters of this layer is a matrix W, and the probabilities are calculated by using softmax W times H. Now, if you look at W, each column in the matrix can be regarded as the embedding vector of a particular label. As a result, the unnormalized score of each output label equals H dot product its embedding Li, namely the column in W. And when we use a softmax function to normalize these scores, we obtain the output probabilities. Given this output layer, the cross-entropy loss can be denoted as the equation at the bottom of the slide. In particular, we use dot product to calculate the similarity between a hidden vector and a label embedding vector, which is denoted as dot S. In this loss, the numerator has the similarity between the gold label and the hidden vector, while the denominator is the sum of exponential similarities between each label and the hidden vector. In the same light, let's look at the contrastive loss in SimCLR. We have a set of different hidden vectors in a batch, and we use cosine similarity, which is a normalized dot product score to calculate the similarities. And the loss has the similarities of positive samples on the numerator and the similarities between all samples in the denominator. By writing the contrastive loss and the cross-entropy loss together, we can find that they both have the same form of an infomax function. The similarities are calculated using different equations. However, there has also been investigations for cross-entropy loss using cosine similarities. A salient difference is the denominator. While the cross-entropy loss makes contrast between the gold label and all possible labels, the contrastive loss takes a few negative examples. Given these similarities, we can summarize a few important things to consider when we design a contrastive learning algorithm, and these have also been the factors that are considered by previous work. The first thing is what to contrast. The second thing is how do we make the contrast? And the third thing is the goal of making contrast. These three items are quite correlated, and let's look at them one by one. First of all, in order to make a contrast, we need to define positive samples and negative samples. Different methods have been used to draw positive pairs of samples. For example, we can translate a sentence into a different language and then translate it back. The pair of original sentence and back-translated sentence can be treated as positive samples. We can also delete some words from the sentence, or truncate the sentence, or replace words with synonyms to make positive pairs. Finally, for neural representations, we can also apply dropout to make positive samples. Matching pairs of data instances are also used as positive samples. For example, an image and a piece of text to describe the image, a query and a document that matches the query, or parallel segments or sentences across different languages can be used as positive samples. Such matching data can also be applied to a given input and a gold output label. For negative examples, a typical way is to draw samples from a batch of training data. Here, some people study the influence of batch size, and some existing work also discussed how to effectively increase the number of negative samples without enlarging the batch size. Negative samples can also be drawn by doing sampling over the instance space. Here, existing work considers how to draw hard negative samples, or negative samples that makes the best contrast between positive samples. Given positive and negative samples, the next thing to consider is how to make contrast. There are different ways of doing this. For example, we can reweigh the contrastive samples. We can use contrastive loss as a regularization term to traditional loss functions. And we can also apply direct contrastive loss objectives. Here, after carefully considering how to measure similarities between a pair of instances, we can apply both max margin loss functions or log likelihood-like loss functions. In fact, these are the two standard forms of contrastive loss functions and are also the two standard forms of loss functions in NLP. Contrastive learning has been used for different goals. One traditional goal is to obtain nice vector representations, typically through self-supervised learning. For example, it has been shown that by using contrastive learning, the feature distributions are more uniform. Recently, contrastive learning has also been used to obtain multilingual representations. A second typical goal is to improve supervised learning. And here, contrastive regularization terms has been added to traditional cross-entropy losses to better shape the hidden space and improve classification accuracies. A third typical goal is to facilitate retrieval, where we match two different types of data, such as images and text. One more typical example is to rank candidates. A baseline model can generate a range of output candidates, and we can make use of contrast to better differentiate the correct ones among them. That concludes our tutorial. We wish that this will give you necessary background and more inspirations for continuing this line of work.